No, yeah,
in a
it
couple
appears.
of seconds.
Yeah, it appears to me that we are live in YouTube. Okay, so let me start. Are you ready, Agnès?
Yes.
Can I start? Okay, perfect. So today we have the pleasure to receive a very good friend of mine, Agnès Ferté, so who is a postdoc in Jet Propulsion Laboratory in Caltech in California. And Agnès is working principally right now on study of dark energy, on the dark energy. So like you say in your page, the late inflation-like period, using the weak lensing information, and especially working on the DAYS collaboration. But before that, you were working on the first inflationary part of the universe, and especially so working on the inflation models and the repercussion on the CMB modes detection, and especially for Planck. So today we'll talk about the testing cosmological models with weak lensing, weak gravitational lensing. And so thank you so much to accept the invitation and to give the talk. Thank you, Agnès.
Thanks a lot for the introduction and the invitation. So I will talk about testing cosmological models with measurements of weak gravitational lensing, using kind of like standard tools. And also at the end, I will also talk about using machine learning to do that. So as an introduction first, according to our standard model of cosmology, the universe has been expanding since the Big Bang, and it first went through exponential expansion that we call cosmic inflation, and we try to see this effect in the cosmic microwave background. And then the universe expansion has been decelerating for a long time. And thanks to many different probes, we observed that the expansion is accelerating again, and has been accelerating for the past 5 billion years. And in our model of cosmology, we say that this is due to a cosmological constant lambda in the Einstein equations. And lambda is the simplest form of what we call dark energy. Dark energy would be a fluid which density doesn't dilute with the expansion. And that describes our observation very well. But the problem is that we don't really understand what dark energy is. So an alternative is to say that actually this acceleration of the expansion might be due to the fact that we don't really understand the equation of gravitation, which is the main force at work at these cosmological scales. So the idea is that the same way we went from a Newtonian description of gravity on Earth to the Einstein theory of general relativity when considering the solar system or galaxy, then on the scale of the universe, we would need a new type of gravitation, a new description of gravitation. And that's a field of modified gravity, where the idea is that we modify the general relativity and try to test with our cosmological observables. So here on the left, I'm showing kind of constraints from different type of cosmological probes, showing that indeed it seems like the universe is accelerating. So you can do that by measuring the distance of things in the universe, but it's actually very difficult to measure distance in an expanding universe. So we need like some specific probes like supernovae, which are like standard candles, or bionic acoustic oscillation, which are like a ruler that you use to measure distances. You can also use the cosmic microwave background, so the light coming from the Big Bang that we can measure today. But what I'm going to focus focus on is another type of probe to measure the growth of structure in the universe, to be able to probe this evolution, this recent evolution of the universe. So the universe has been expanding since the Big Bang, and started with tiny fluctuation of density, of matter density, with a density contrast of 10 to the minus 5, which have been imprinted on the cosmic microwave background, which we can see here on the left. And after this whole evolution of the universe, this tiny fluctuation evolved into the large-scale structures that we see today, which form what we call the cosmic web. So it's a cosmic web of matter that's forming clusters and filaments, etc. And this evolution of the growth of those like density fluctuation to those large-scale structure depends directly on the content of the universe, so dark energy, and on the laws of gravity. So by measuring the growth of structure, you can measure dark energy and test for the laws of gravity. The problem is that most of the matter in the universe is not visible. So 80% of the matter is dark matter, which is a matter that doesn't emit any light, but we see its gravitational impact. So we need to find an indirect way to probe those invisible dark matter structure and their growth with time. So one of these probes is the weak gravitational lensing. So gravitational lensing is the deviation of light due to a gravitational potential that will curve space-time, and so the lights will follow this curve. Weak gravitational lensing is the fact that the light coming from faraway galaxies will be deviated due to the curvature of space-time caused by the gravitational potential of this cosmic web, these dark matter structures. So the impacts of this weak gravitational lensing is first to magnify the image of those faraway galaxies, but most importantly, it's also changing the shape of the image of those galaxies. So, okay, we can't see these dark matter structures, but we can see its impact on the images of those faraway galaxies. The problem is that we don't know the intrinsic shape of each galaxies. So we have to do a statistical measurement, measuring hundreds, or actually we measure millions of galaxies to be able to pick up this signal. That is just like a 1% distortion of the shape of galaxies. So it's a very, very small signal, but by measuring the shape of many, many galaxies, we can pick it up. And we measure this distortion of the shape of galaxies at different redshifts, and that's how we can measure the growth of the underlying dark matter structures. So that's the concept of weak gravitational lensing. And to do its measurements, we use galaxy surveys. So we image galaxies, and we then separate this image of galaxies between two types. One type is what we call source galaxies, for which we will measure the shape. And the other type is lens galaxies, for which we measure the position. And actually, a lot of the most part of the information of the impact of weak gravitational lensing is contained into a simple 2-point correlation function. So we just actually need to correlate each galaxies with other galaxies as a function of their distances to pick up the signal. You could also look at correlating like 3 galaxies and doing that for every galaxies. But actually, if you just do that with pairs of galaxies, it's enough to pick up most of the information. So the first type of statistics of 2-point correlation function that you can measure with these galaxy surveys is what we call the cosmic shear. So in this case, you correlate the shape of the source galaxies. And in this way, you will be sensitive to you will be able to probe the invisible dark matter structures between you and the source galaxies. So it's a way to probe dark matter distribution in an unbiased way. So how do you do that? Actually, the shape of galaxies, you describe it by 2 ellipticities. And because you need 2 numbers to describe an ellipticity, so E1 and E2, you measure that for every galaxies. And then you do the correlation between these ellipticities as a function of the angular distance between galaxies on the sky, this angular distance theta. A very important point is that you have to measure quite precisely at which distance those galaxies are, because then weak lensing will the impact of weak lensing will depend on the distance of those galaxies. So that means you need to estimate quite well the redshift of those galaxies. Because we use what we call a photometric surveys, which means that we just have like 4 or 5 filters. So we will only be able to measure the spectra of galaxies in 4 or 5 optical filters. And we have like a coarse sampling of the spectra of galaxies. It's a very difficult task to do that, to be able to measure redshift from this measurement of galaxy spectra. But people work hard on this, and that's what we call the photometric redshift, which I think Sébastien talks about during this call. And basically, people are able to associate probability of galaxies to be at a given redshift. And so we separate this population of galaxies into, in this case, 4 redshift bins. So from the closest one to the most distant one. And then you do correlation of the shape of galaxies that are at different redshifts. So that's why you will often see the cosmic shear measurements for correlation at different redshift bins. So here, for instance, it's correlating the closest galaxies with the closest galaxies. And here, for instance, bottom left, it's correlating the shape of the furthest galaxy to the closest one. And so that's by doing this, what we call tomographic cosmic shear measurements, you can infer information about the properties of the universe. And here I want to show how this 2-point correlation function, this cosmic shear observable, varies with, for instance, one of the cosmological parameters of the standard model is omega m, so the energy density of matter in the universe. So if you have more matter, that means that you will have like a higher signal of weak gravitational lensing, and that will give a higher amplitude of this cosmic shear as a function of the angular separation of theta. The second type of statistics that we measure from galaxy surveys is cross-correlating the shape of source galaxies with the position of lens galaxies. And by doing this, basically what you do is you measure the tangential shear of faraway galaxies caused by the dark matter structures that your lens galaxies are tracing. So this is a bit more complicated because you're using galaxies to trace the underlying dark matter. And the third correlation that we do is correlating directly just the position of lens galaxies. So this is another way to probe the dark matter structures, but by only using galaxies to trace dark matter. So in this case, like galaxies are like the visible tip of the iceberg, basically, where the invisible tip of the iceberg is the big dark matter structures in the universe. So what we do is to combine those three types of two-point correlation functions. And that's very useful because, for instance, we, as I was saying, that the galaxies are like the visible tip of the iceberg. The thing is, like, we don't know exactly the relation between galaxies and dark matter. Like, we don't know how many galaxies we should expect for that much dark matter. That's what we call the galaxy bias. So if you were just using the galaxy clustering, you wouldn't be able to infer information about the universe because you have this unknown galaxy bias relation. So, but the cosmic shear is directly probing dark matter structures without like the need of tracing dark matter with galaxies. So that's not sensitive to galaxy bias. So that's why by combining all of that, you can break degeneracies, for instance, on the galaxy bias. And the cosmological parameters that this combination of observables constrains the most is noted S8, which is a combination of sigma 8, so the fluctuation, so the variance of the density fluctuation in a sphere of 8 megaparsecs, and omega m, the energy density of matter, with some power. So this is the parameter that is most constrained by weak gravitational lensing and clustering. So we often quote our results on this parameter. So I actually have joined the Dark Energy Survey collaboration in 2014. So the Dark Energy Survey is a galaxy survey, and one of its goals was to measure weak gravitational lensing. It was using the camera DCAM at the Blanco 4-meter telescope at CTIO in Chile. And one of the power of this camera is that it has a huge field of view, so 2.2 degree field of view. And thanks to this big field of view, we were able to image 10% of the sky between 2013 and 2019 in 5 optical and near-infrared filters. So 10% of the sky is one of the largest part of the sky measured by a weak lensing survey. And DS also has a huge legacy because we had more than almost 700 million astronomical objects detected. So because it has so much data and it's a very difficult analysis, it also means that we need a lot of people. So the Dark Energy Survey collaboration is an internal collaboration with the US, Brazil, the UK, Germany, Spain. I think that's it. And with 700 participants. The cosmological probes that are measured with the Dark Energy Survey are first those geometrical probes that I was telling you about at the beginning, which are supernovae and baryonic acoustic oscillation, and probes of the growth of structures. So as I was telling you about, those 3 by 2 point measurements, so weak lensing plus clustering of galaxies, and also galaxy clusters. So using weak lensing and clustering, we have done 2 cosmological analyses, And we are working on a third one using all the data. So the first cosmological analysis we published 3 years ago now, using the first year of observation. This year, we released the results from the 3 years of observations, and I'm going to show you those results. So from the first year of observation of the dark energy survey, that meant that we used 1,500 square degrees of our footprint and 50% depth. So in blue here, this tank shape, that's the footprint of the observation of the dark energy survey. And in red is what we imaged during the first year. So the galaxies that we use to do the measurements of the weak gravitational lensing, we measured the shape for 26 million galaxies. And we did those measurements of the cosmic shear shown here on the right. So recently we have done the next step. So using the 3 years of observation from the dark energy survey. So now we're using the full footprint, so the 5,000 square degrees part of the sky at 50% depth. And so with the next cosmological analysis, we'll be able to use this full footprint and the full depth. But for now, it's just half the depth. But this is already a huge step because the shape catalog, like the catalog of the galaxies from which we will measure the weak gravitational lensing, is the largest shape catalog to date with 100 million galaxies. These are the measurements of the cosmic shear. So again, in the source galaxies are divided in 4 redshift bins. So we have all of those correlation for the shear. And up to now, I just showed you this Xi plus quantity, but there is also another quantity called Xi minus. So those are our measurements of the DES year 3 cosmic shear. So in SECO here, what you see are the measurements, and the black lines is the theoretical prediction for the best fit cosmological model. So the whole goal then, once you have those measurements, is to compare those theoretical prediction of the cosmic shear to the measurements to infer the value of the cosmological parameters. So to do that, we take a Bayesian approach, and we use parameter estimation codes, in particular Cosmosis and Cosmolike. So you might end up using one of those codes if you end up working on weak gravitational lensing. So basically, those codes for a given set of cosmological parameters, you will be able to compute the cosmic shear signal and also the clustering signal, etc. And you repeat this process for different input values to check what is the favored values of those cosmological parameters. But we don't only vary the cosmological parameters, because that's only like 5 or 6 parameters, which is not many at all. You actually need to vary also what we call nuisance parameters. So those are used to model all the systematic errors that can impact the measurements. For instance, if you misestimate the photometric redshift, that could impact your cosmological results. So you need to take that into account in this analysis. And same for other type of systematic errors. So we need to vary those parameters. And this step of doing the Bayesian analysis is very computationally intensive. So we need to use high performance computing systems like NERSC. And for that, we use, like, for instance, 200 processors for like a day to be able to go from the measurements to those measurements of the cosmological parameters. So this is showing in blue the results of this Bayesian analysis on omega m and S8, and also sigma 8 here on the top. And in yellow, the results from the clustering and the galaxy-galaxy lensing. So we had to test that we would be that those two measurements are consistent, and then if they are, then we can combine them. So we checked that they were consistent, and so we were able to measure cosmology from this combination of two-point correlation function. So those results are shown here in black. And this is very exciting because it's the most powerful constraint on S8 from a galaxy survey. So to obtain those results, there is a lot of underlying work to go from the image of galaxies to the cosmology. So you have to do, you have to work on the images, characterizing the point spread function, doing constructing the shape catalogs, also measuring the redshift distribution, which is a very tough topic, as I was telling you about. You also have to take care of other possible observational systematics. You also have to make choice about which model you will use to model the 3x2 points function. You have to make simulation to test your analysis. And from there, finally, we do the measurements of the 2-point function, and then we get the cosmology to end up with our cosmology from the weak lensing plus clustering. So this is a huge amount of work from many, many people, and a lot of papers came out of this huge work, and this is a list of papers that came out recently from the 3 years of observation from DES. And one of the key measurements, one of the key points is that we are able to compare the constraints from DES to constraints using the cosmic microwave background. So the light coming from the Big Bang measured by the Planck satellite. So here we're asking, okay, do we see the same universe when we observe the lights coming from 13 billion years ago to when we observe galaxies in the past, like 5 billion years? Do we see the same universe? And so do we measure the same values for the cosmological parameters? So it turns out estimating this consistency between two measurements is a complicated question, because actually there is not just two parameters. There are many parameters, as I was telling you about. Actually, we are varying 31 parameters. So it's when we show it in just on S8 and omega m, this is just a projection in two dimensions, but they're actually, it's actually like a 31 dimension parameter space. So how do you estimate the tension? People have worked on different metrics to estimate this tension. And we chose some specific metric where we decided, where we saw that the tension between measurement from the Planck satellite and DES is 1.5 sigma. So that's using the tension metric called the parameter difference. So it's a parameter difference, but taking into account the multidimensional space. And 1.5 sigma for us, it's not a tension. So it seems like we are we are consistent with measurements from the Planck satellite. So this is further affirming that the standard model of cosmology seems to be very powerful and correct. So one of my main work is to use the weak gravitational lensing to do cosmological tests of gravity. So now it's, instead of focusing on the lambda CDM model or the value of the equation of state of dark energy, now we're asking, is general relativity the correct theory of gravity to describe cosmological scales? So for this, one of the way we do that is by taking what we call a phenomenological approach. So it's not like a real theory. It's really parameterizing the equation of gravity and measuring those parameters from our observation directly. So in particular, what we do is we modify the way light reacts to a gravitational potential by this function sigma that depends on time and scale. So that's the weak lensing equation. And this is a Poisson equation, and we modify the way matter reacts to a gravitational potential by a function mu that also depends on time and scale. So you add sigma and mu in your Bayesian analysis, you fit for sigma and mu, you do their measurements. If you see that they are consistent with 0, then that means general relativity seems to be correct on cosmological scales. But if you measure any deviation from 0, that means there is a hint that general relativity is not correct on those scales. So it's a very powerful way to test gravity because you're directly, it's directly related to your observables. Because as I say, sigma is telling you how the light reacts to gravity, which is directly linked to weak gravitational lensing, because weak lensing is the deviation of light by gravity. So with weak lensing, you can directly measure sigma. The problem of this approach is that you have to choose a given parameterization for sigma and mu. So what people have done, and we have also done in GS, is to take a time-only dependence of sigma and mu, where it depends, basically is parameterized by the energy density of dark energy. And what we measure is sigma naught and mu naught, which are the value of sigma and mu today. So here again, I wanted to show how cosmic shear depends on sigma naught. So again, I'm showing the 2-point correlation function as a function of the angular distance, theta. And for higher sigma naught, you have a stronger gravity, so you have a higher amplitude of cosmic shear. So you see that by measuring cosmic shear, you are able to put constraints on sigma naught. You would be able to put constraints on sigma naught. So my work in particular was to do the numerical implementation of the impact of sigma and mu on the theoretical prediction of those 3-by-2-point function, so weak lensing and clustering. I did that specifically in the context of the Cosmosis code. Then we have to do a lot of tests to test that our analysis is robust against systematic errors, because if we show sigma and mu different from 0, we want to be sure that it's not because we forgot that there is some systematic errors or that we haven't modeled it well or anything. So this is a huge step, and it's one of the power of doing those analyses within an experiment, is that we go very deep into the possible systematic errors that can impact our analysis. And it's also very difficult to do that because it requires doing a lot of those Monte Carlo Markov chains, the chains that are doing the Bayesian analysis. And they take even more time than in the lambda CDM model, because the parameter space is more complex, because in addition to these cosmological parameters and nuisance parameters, we also have the sigma naught and mu naught parameters. And each step of this Bayesian analysis is also taking longer, like computing the 3x2 points observable at each combination of those parameters takes a lot longer. So this is a kind of difficult step, but with many people, we were able to do it for the first year of observation. So those are the results that we published 2 years ago. And this is our test showing that indeed our measurements of sigma naught and mu naught are not impacted by possible systematic errors. And we did this test on simulated data of the 3x2 point observables. We didn't do that on real data, because one key point of our analysis is that we don't want to see the final results from the data on sigma naught and mu naught until we are sure that we passed a whole bunch of tests showing that our analysis works well. So that's to avoid what we call confirmation bias. And it's a very important step to be really sure that we are not informing the analysis because we want to see a given results in our final constraints. So because we were able to check that our measurements were not impacted by systematic errors, we were able to show the final constraints on sigma naught and mu naught from the first year of observation of DES. So these are the results shown in blue. And that was a very powerful measurements because first it showed that DES could actually measure sigma naught, that sigma naught is consistent with general relativity, which is 0, yeah. And it was the most precise measurement of sigma naught by a galaxy survey at the time. And then we combined these measurements with other type of measurements like baryonic acoustic oscillation, supernovae, and measurements of the cosmic microwave background to obtain the right contour here. So yes, general relativity seems to be still holding, let's say, on cosmological scales, but there is a lot of improvement that we can make to tighten those error bars and see, like test even better if there is any deviation from general relativity or not. So to do that, we are now working on doing the same type of study with the dark energy survey 3 years of data. And in particular, I'm co-coordinating with Jesse Muir at Stanford, the team that is testing model beyond the standard model of cosmology. And in particular, I'm leading the test of gravity. So this work is ongoing, and also it requires the help of many, many people, and a lot of them are like you, PhD students, and there are also postdocs. So yeah, a lot of the work is done by early career scientists. And it's very exciting to be working on this because it's, as I was saying before, it's very new type of data because of this large number of galaxies that was observed. So we're going to constrain models like testing if dark energy changes with time, we're going to check if the growth of structure has been also changing with time. We're going to test if the universe really is flat, if there is any type of other type of neutrinos than the standard 3 neutrinos. And we are doing tests of gravity, similar to what I've shown you, measuring sigma naught and mu naught. But we are also going to do other tests of gravity. So we are doing updates to the pipeline to do correct theoretical prediction of the 3x2 point measurements. We are doing a whole bunch of validation tests to test that our analysis is robust against systematic errors. And finally, we will do the final analysis. So this is very much ongoing, and I hope we will have results this year. And we expect an increase of 30% of constraints on sigma naught. And these are results obtained from simulated data on W naught WA. So this is work ongoing, yes, and I hope you will be able to check the results when they come out. Then looking further down the line, there is, after a DES, a new generation of galaxy surveys will be imaging the sky. One of them is LSST, which is a survey that will be done by the Vera Rubin Observatory from Chile as well, actually a mountain that just next to the mountain where the blancoformeter that were used by DES is. There will be also 2 space missions, Euclid from the European Space Agency and Roman from NASA. So they will all be coming in the next decade, and already with DES, we are kind of like the step between like smaller weak lensing survey and those huge surveys. And in one of my papers, I've shown that we expect an increase of 1 order of magnitude on the constraints on sigma naught and mu naught with the LSST galaxy survey. So this is a huge improvement, but it's also very challenging because we have to model the systematic errors very well, and also doing the measurements themselves is also very challenging. Another challenge that I want to talk about, and I've been working on in the past year, is that if you want to test gravity, you can do as I presented before, to measure those 2 parameters, sigma naught and mu naught, or you can choose to look at a specific modified gravity theory, and then do the Bayesian analysis and measure if this modified gravity is preferred compared to GR, to general relativity. The challenge is that this is a famous slide from Tessa Baker, specialist of modified gravity, showing many ways that you can change gravity. You can choose to have more than 4 dimensions. You can have a new field, and it seems impossible to be able to test a lot of these theory, because each of them takes a long time, and also you need to design numerical simulation for those theories to be able to test your analysis. So it seems like it would be impossible to test them all, but you also want to test as many theories as possible, because you will have this amazing data coming. So the idea is to try to simplify this theory space using dimensional reduction algorithm. So this is work I've been doing with a specialist of self-organizing map, which I'm going to describe just after, a student and 2 cosmologists at JPL. And we obtained grants from JPL to be able to do this work. And we submitted the paper to physical regulators a few weeks ago. So I'm going to show you the results that we obtained. So dimensionality reduction algorithm are algorithms that will help project a multidimensional space into a smaller space. So in general, we use a two-dimensional space. So that's just, just like a 2D map, for instance. There are different types of algorithms, but we will focus on self-organizing map. The idea is that this is a very schematic view of what a self-organizing map does, but basically it will project a multi-dimensional space by putting the data that looks the most alike together, the closest. So for instance, if you gave a self-organizing map images of paintings, it would recognize the faces and would put them together, and would recognize trees and will put them together. And then in the middle, you will have things that look both like face and trees. So this is self-organizing map is unsupervised learning algorithm. And basically it works by starting with a grid of basically.
Just we have 2 minutes, sorry.
Okay, great, thanks. Yeah, a grid of vectors where you would be able to update the weights of each vector to see which vector of the grid looks most alike to the data. And you repeat the process until your grid represents your data space very well. So we did this for modified, for where the input is not paintings, but cosmic shear prediction for different modified gravity theories. And this is the results that we got, where you have this map where each pixels correspond to places where the cosmic shear looks the most alike. So this is for general relativity. But here I'm showing, for instance, this part of the map corresponds to one type of modified gravity theory. And this part of the map corresponds to another one. And then you can test if, for instance, testing for a time-dependent dark energy gives you the same, is the same as looking at F of like another type of modified gravity theory. And it's very simple to use this tool to test that and show that indeed you would need to constrain those two types of theories with future surveys because they have a different impact on cosmic shear. So I've shown that the DES 3 years of data are giving very competitive cosmological constraints that we faced many challenges, but we also solved those challenges, that we are working on constraining those more cosmological models, and also that you can have one type of use of unsupervised learning to guide future analysis to test cosmological models. And also, although we measure that the dark energy survey is not in tension with measurements from the cosmic microwave background, it's still in line with the fact that weak gravitational lensing survey measure S8 smaller, like consistency smaller than what is observed by the Planck satellite, for instance, for the CMB. So it will be very exciting to see what LSST, Euclid, and the Roman telescope would give in the future. So it's very exciting to be working on those on this right now. Thanks.
Thank you so much, Agnès. Very, very nice talk. Thank you. And sorry, I don't think we have a lot of time for questions. Okay. Maybe we can try to have one. If someone have a question, please raise the hand. And because it is in English, maybe they are a bit more shy.
Yeah.
But just
I have yeah, there is one from Luz. Please go ahead.
Luz Garcia, you have a question.
Okay. Thank you. Very nice talk, Agnès. Thank you. I'm wondering if you think there is something like that we can say behind these tensions of the Hubble constant and the sigma 8 in terms of like physics beyond the standard model, or it's just that at this point our different cosmological sets are not like having a match for different reasons, systematics or some other sources of discrepancy, or if you think there is something like beyond this model and the physics that we know so far.
Yes, yeah, thanks. So testing those models beyond lambda CDM, like testing gravity or testing neutrinos, etc. It's also to see if we can solve this tension with those models. And so far, we haven't seen that you can solve this tension with that. But that I think we will see even better when we will have more constraining data. Because for now, it's not constraining enough, as I think, to see if you can solve the tension. So yeah, I think in the future, it will be more clear if it comes from beyond lambda CDM or from like a systematic errors.
Thank you, Agnès. I don't think so we have, because the next lecture we start in 2 minutes. So, but it was very, very, very interesting. I have a lot of questions, so maybe we can make a Zoom in another day during the holidays.
Sounds good.
to discuss.
Okay.
So
I'll stop sharing my screen.
Yes, thank you. So it was a very nice talk. Thank you.
Thanks.
Thank you to accept the invitation, even for the very, very early time for you. But I know you woke up very early, January. So. So perfect. So thank you so much. It was a very, really, real pleasure to see you.
Yeah, thanks a lot, everyone.
Okay, we are in touch.
Thank you very much, Agnès.
Thanks, Agnès. Bye-bye.
Thanks, bye.